Ladies and gentlemen, we'll begin the last session of this program of remembrance and celebration of Atle Selberg, and we will have contributions from family and friends, from Dennis Hejhal, Erik Hjorth-Hansen, Betty Compton Selberg, Ingrid Selberg, Lars Selberg, and Niels Bass. I'll begin by asking Dennis to give his contribution.
Okay, thank you. It's an honor for me to be invited to speak today at Atle Selberg's memorial. And before I go over to the overhead projector and discuss some math, I'd like to say a few words about Atle, some notes that I made here. I first met Atle about 34 years ago, in December of 1973. When Atle passed away this past August, I lost someone who was, for me, not only a wonderful mathematical colleague and mentor, but also a dear friend. And like I said in an email to a few people a day or two later, for me, Atle was not only a great mathematician, but a great human being. I also have to say, over the years, I was invited into the Selberg home so many times, thanks to Hedges and Mickey's hospitality, that in ways I almost came to feel like a member of the extended family. And I feel extremely fortunate to have gotten this chance to get to know Atle the way I did. When I flew into Princeton the other day from Minneapolis, I was thinking to myself, if someone asked me just one word, to say just one word or of just one word to describe how Atle affected me over all these years, I think the word I would say is inspiration. I first experienced this effect when I was at Columbia in the 70s, and Atle and I were meeting regularly, about once every week or two, as I prepared volume 1 of my book on the trace formula. And I remember how after we got done discussing math, I went home always so very, very inspired to work. And, I was 26 years old then, and it's strange that even 30-some years later, whenever Atle and I discussed math, he still had the same effect on me. And I'll miss that. For my tribute today to Atle, a couple of people suggested that what might be nice, especially for the family members here and non-mathematicians this afternoon, what would be nice would be for me to give a blend of a number of personal reminiscences of Atle and put that together with, a 10 or 15-minute layman's explanation of the trace formula. This morning we already heard something at a technical level about the trace formula, but I'll be at a much, much lower level. So I think now is a good time to go over to the overhead. And in layman's terms, we can ask then, what is the trace formula? Let me do this. Now, in its simplest two-dimensional form, the Selberg trace formula is a deep relationship between musical frequencies of certain types of drums and lengths of taut rubber bands stretched out on those drums. So, if we took, for instance, two drums in the XY plane, we view them as vibrating membranes, then what we know, just general everyday experience, that each drum has certain natural frequencies of vibration. Kappa 1, kappa 2, kappa 3, and these numbers increase up to infinity. They're positive numbers, certain frequencies, depending upon the shape of the drum. Maybe there's a hole in it, maybe not, And if you're banging on the drum and looking at the actual vibrational motion, then this will have the form some function of x and y times this sinusoidal term. There's a thing going up and down. And the un, function of x and y, we can think of it as kind of like an amplitude or a signed amplitude of the oscillation at each point x, y. And of course, as you change the n, the pattern changes. And we call this function an eigenfunction. Now, you could also take a drum that doesn't have any edges. You could have one like this. Take a donut. Let me push this up all the way. Take a regular donut. That green in there is just to show the dimensionality of something to hold on to there. And again, even for a donut, this thing starts vibrating, you're going to get some frequencies, list of frequencies, positive frequencies, kappa 1, kappa 2. And the actual vibrational motion would be un times this sinusoidal term. Now, to see this case better, it's helpful to flatten the drum out. And what you do is just this. I mean, note the green there. You put it back up here. Just add another curve here, the red one, and then make a cut along the green line. Well, if I do that and then open this thing up, I'll get this figure clearly. All right? This is our drum. It's now cut once. If I now cut along the red line, okay, and finally open that up, then I'm back at a rectangle, but in this rectangle, of course, the green corresponds to the green and the red corresponds to the red. Okay. So in this way, we can view our drum as one brick, a piece of tile, a tiling of the xy plane. Just put all these rectangles together. And if you bang on this thing with the understanding that the green is always in lockstep with the green and the red is always in lockstep with the red, we still then have our vibrational motion as this function un, this amplitude, times this sinusoidal term. And of course, as everybody knows, you can have tilings of the floor with other shapes besides rectangles. Why do I mention this? Because, I mean, what if you had a donut? If you have a donut, my thing's out of order here. Sorry. I was putting them in the wrong pile. It's not that big of a pile. If you had a donut with 2 or more holes, let's say 3, again, it's still the same thing. You have the frequencies, you have the vibrational motions, but in this context, when you try to do this flattening, you need to flatten into a non-Euclidean or Poincare plane, which we just understand to be either a half plane, y greater than 0, or just the inside of a disk like that. And then the edge, that's regarded as like the point at infinity. Okay, so if you do an analogous thing, make appropriate arcs and cut, then you get a tiling of these planes. And so, and they look somewhat like Escher plots. So you have something like this, for just as an example. Maybe in our example, the drum D, it might be some triangle, or it could be a finite collection of these triangles, and you piece these things together, and then you use that as the brick, and you cover the whole non-Euclidean or Poincare plane. Here's the Escher analog. Probably most of you have seen this type of thing. This is modeled on that idea, and this tiling. Here's one that's very appropriate for people studying prime number theory and trying to make connections with zeros and primes and zeros off the line and whatnot. Again, it's one of Escher's. But now let's go back then to the original drum. Let's say we still have 3 holes. And now do what I said. Take some rubber bands and then just put them, and we assume that these bands, they're taut, but they adhere to the surface. So I've just shown a few examples of ways that we could string the rubber bands in there. Notice the red one here. This thing doesn't collapse because it's adhering to the edge of the drum here. And these are just a few simple ones. I can start building up more complicated patterns where these rubber bands start crossing. Just made one there. Okay. And basically what I'm saying is you put these rubber bands on here in every way in which you can go around Robin's barn. So if you do that, then you get another list of lengths, L1, L2, L3, and so forth, and those lengths get longer and longer as the rubber band gets more and more, it's wrapped up. And in the simplest form, in the two-dimensional form, the trace formula is a formula that relates these frequencies simply to these lengths. This is what it is in its simplest form. Now, it's not a one-to-one formula, like you give me the kappa and then out pops the corresponding L. No, it's a formula that looks like this. You would have like two functions. For the next, in this transparency, I assume maybe you know a little bit about calculus, but if you don't, you have two functions that are related in some way, some reasonable functions. And it's a statement that when you take the sum of all these terms involving these lengths, that you get another sum involving the frequencies plus a certain constant. And that constant is obtained by integrating one of these functions that you start out with. Basically, it was using calculus operations. Now, if you don't know any calculus, it's possible that this is it's too high level. Let's go lower. Let's just take an example. This is closer to Atles' heart, so to speak. Take these lengths and take this famous number. If you've never heard of it before, just think of it as 2.718, and take e to that power. So call this new thing that you get pj, capital PJ. One of the cases, I said you plug in these functions, one of the cases of the earlier formula with the g and h, it simply says the following. If you count the number of these pj's on your drum, which are less than x, then it's given by x over log x plus, and here's the term where I'm summing these frequency terms, plus 2 times square root of x over log x, and the sum of these sinusoidal type terms divided by the kappa. Now you have to remember the kappa is very, very large. It's 10 to infinity. The sine is only plus or minus 1. These terms are very, very small, so this sum is finite. And plus dot, 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 there's some smaller terms in there. Now, of course, I have to say something. In this talk, please, the experts should either cover their ears in places or just take out, I don't know, 100 grains of salt. I'm just trying to give the big picture. All right. When x is large, then square root of x is much smaller than x. And so what we see here is this. For any Escher-type drum, if we use this formula, the number of pj's that are less than x would be about the biggest term there, which is x over log x, when x is large. And in Enrico's talk, earlier this afternoon, we saw the formula, corresponding formula, the x over log x, involving the primes. Recall that the number of primes, ordinary prime numbers, 2, 3, 5, 7, etc., this too is approximately equal to x over log x when x is large. And it's like on these drums, these numbers pj, they're trying to imitate primes. Now, if you go back and look at this more carefully, and again, this was touched on in Enrico's lecture, the second formula I'm going to show here. Let's just back up for a minute. Atles' trace formula, the special case of the trace formula, tells us that the number of pj's less than x is this term, and then plus this sum here, and here's the square root of x over log x. But remember that Riemann's great contribution was that with his Riemann zeta function, complex numbers, he found a formula that the number of p's less than x is x over log x, and then the next term, the correction term. And if you wrote that out, Enrico didn't, I mean, you get it from doing a little further calculation, you get a very similar looking term here involving signs and these numbers gamma n, and these numbers are associated with those points where the zeta function, the Riemann zeta function, has zeros. I mean, if the Riemann hypothesis is true, then these gamma n's should be positive real numbers, and the zeta function should just vanish along the half line. Okay? And I recall the definition of the zeta function here. This is for s greater than 1, and we extended it to complex numbers in a natural way. Well, the formulas, they look very similar except for the sign. So this similarity is so strong that even with that plus or minus sign, you can push through and develop an analog of the Riemann zeta function for each drum D. And this is called the Selberg zeta function. The Selberg zeta function will have its roots at exactly these points along the half line that are associated with the frequencies of the drum. And because of this sign difference, the plus or minus sign difference, I mean, the formula, this is not quite correct, but it's enough. You just basically turn the zeta function upside down. Here's the Selberg zeta function for s bigger than 1. You extend it in a natural way. When you see these analogies, it's natural to wonder, can there possibly exist some very special, miraculous drum, a D0, in some kind of tiling setup, either this one or some other thing, where the frequencies of that drum can actually match these numbers, gamma n, which we hope are positive real numbers. Does such a drum exist? And this is a famous dream of Pauli and Hilbert dating back to about 1920. They speculated that maybe the Riemann hypothesis, the famous Riemann hypothesis involving the Riemann zeta function, is true because the gamma n's are simply a frequency. Now, you wonder, well, you know, this dream and this dream drum, it would have to be the most miraculous drum in the world. It would be very, very surprising if the thing just turned out to be an ordinary donut with 3 holes. You'd be shocked. And of course, I mean, there are some snags in this. If you look at these donuts and look what's going on there, what I said, there's some. You have this with these Escher type tilings. You always have this plus or minus sign snag. If you look at these numbers pj, they're 2.72 to the lj. They don't really have any close connection to the ordinary primes. And still worse, here's another case of the trace formula. If you ask how many frequencies are less than t, you get this I term, which is, in this case, constant times t squared, and then plus the sum of the analogous part, and this time with the pj's. Now, already in Riemann's time, it was known that the number of gamma n less than t is like t log t. Even the first term doesn't match. It's completely the wrong order of magnitude. So clearly there's some snags. And I might just mention then that you say, well, maybe you shouldn't be using drums of exactly that type. This is a well-known thing in number theory. You can get, you might say, drums where these PJs look like they're a little more closely related to ordinary integers and primes. If you stretch out the drum and like pull off one of the ends, the ends there with one of the holes, and finally go way to the limit, and pull it all the way out to infinity. I think I have a here. So pictorially on the tiling, so all you're doing is you're just taking that original triangle that I started with, or some combination of that. You're just taking one of the ends and pulling it out to the edge. You can work out the trace formula in this case. And you get a similar formula, but you get some new terms that arise from, because you pull this thing out to infinity. But to make a long story short, you still have all the same snags there, in particular the t squared versus the t log t. So this doesn't really look very promising. But you just wonder about something here. You know, it's not yet clear whether this dream drum of Pauli and Hilbert actually exists. And you just wonder at Atles' 1956 paper on the trace formula, there were also, as I said, we were just doing dimension 2, there are certainly trace formulas for non-Euclidean spaces and tilings where the dimension is greater than 2. What about vibrating objects in 24 dimensions or something like that? Could you possibly get something there? Although Atle never said this in print, he told me in the early, well, I guess it was about 1974, and then more recently, a few years ago, that throughout all of his work on the trace formula, he never thought that any of the trace formulas in the 56 paper associated with the Riemannian symmetric spaces would ever say anything significant about the Riemann hypothesis. And he liked to tell me that in all of his life, he only had one idea that he thought might possibly lead to the Riemann hypothesis. That was in the early 50s. And he couldn't get it to work, and he's not going to tell me what it is. So, but it's not the trace formula. It's not the trace formula, he said. So, all right. Now I think this is enough on the trace formula. I want to show some pictures using this PowerPoint presentation. After I finished volume 2 of my book on the trace formula, one of the things I started wondering about, because Atle said maybe for the Riemann hypothesis you'd have to look at a more general class of functions, and certainly one of the functions that's very, very important in the Selberg trace formalism are these eigenfunctions UM, these amplitudes. And I developed computational techniques for plotting these things to high precision. So for his 75th birthday in 1992, I gave him a picture of one of these. I have to get rid of this. This is the color coding indicates the relative size of the UN. So the cap is about 125. Red is very high positive. Green is a little less positive. Yellow is essentially 0. Light blue, a little bit negative. Dark blue, very negative. And as you can see in this pattern, I mean, you do find, oops, sorry, wrong button here. You do find certain ridges in here where the thing goes up and down, up and down, up and down, certain patterns. Anyway, this is I presume it's still on his wall in the office. A few years later, when I was in Uppsala, I used our small Cray computer and a new algorithm to compute an analogous picture with a much larger frequency, about 6,000. And I got that, something like that. And in this picture, in the color coding, the lightest color is essentially 0. The lighter green, I took out any distinction between plus and minus. So the lighter green is kind of medium and the dark green is high. You still see these clear, oops, I'm going to turn the whole thing off. Right. You still see these arcs of some kind of ordered arcs all over the place. It looks kind of like a leaf. And there's a lot of things about these functions like this, the UN, that the trace formula doesn't tell us anything about, and a lot of unanswered questions. We don't understand what these ridges are in here. Another thing we don't understand is if you make a box in here, let's say here, some little box, and you look at all the pixels in this picture, and you plot their numerical size, and I'm allowing negative numbers now. What you find is a distribution of sizes. You have a zillion pixels. You find a distribution of sizes that looks very much like students just guessing randomly on some test. You find this famous bell-shaped curve experimentally. We have no idea why that is true. Atle was actually quite pleased when I decided to spend part of my time each year in Uppsala. It was starting in 1994. He had visited Arne Berling there in the late 30s, and he had very fond memories of his visit in Uppsala. He actually came to visit me in Uppsala 5 times, 2 longer visits in 95 and 97, and the 3 shorter ones in 96, 98, and 2000. In the next picture, here's a picture of him as we would walk around town. Oh, I stayed here. This is his old hotel, Hotel Yillet. And we walk around. Oh, I stayed here. I was in this shop, and so he clearly enjoyed it. In the next picture, he came. Let me explain what this is. He came to my professor's installation lecture in October of '96. That lecture is given in a big auditorium in a very old-fashioned and formal setting. I have to be dressed up in tails and a white tie, and it's to a general audience. The Archbishop is in the audience, the governor of Uppsala is in the audience, and most importantly, I have to give the lecture in Swedish. That was a problem. And Atles said, I better come to give you some moral support. You can see him here. He's sitting here with Margit Rees, Marcel Rees's daughter, an old friend of Hedges. Here I am coming in. Okay, and then I give the lecture up on the podium. After this thing, let me explain this. After, the day after, we had a very, very nice dinner that evening. Atle lectured earlier in the day on the history of the prime number theorem. Then I gave my installation lecture. We had a great dinner. My mother was there. It was in a very good mood. And the next day, he said, let's do some sightseeing around town. We went over to Gamla Uppsala, old Uppsala, and decided to have lunch there in one of the restaurants right close to these burial mounds. And the woman at the lunch restaurant was not in back of the cash register. And Atle noticed that there was a helmet up there. And he said, oh, look at this. And so he just went back there. And here we have him in good form. It almost looks like he's saying, may I take your order? Okay, here, no. All right. Now let's see what the next one is. In the next one, of course, when Atle was in Uppsala, he was in Sweden, he was invited to a lot of other places. And one of the places he was invited to was the Netaji Leffler Institute. This is a picture from 1995 in front of the Netaji Leffler Institute where he was giving a lecture that day. He was invited back. This was in 2000. This was, I think, for a lunch. So here we are, basically the same position, Mickey. And we took some pictures inside, and these are kind of interesting. Here's a picture in the library there, which is kind of nice. You know, with Atle, it was mentioned that he was very strong in his opinions and had a lot of self-confidence, and you never, it was dangerous to disagree with him. But he always told me, and I picked this up from what he told his son Lars, he said that a young person should always question authority. It's a good idea. So whenever I had some concern, maybe a little disagreement, I said I'm questioning authority. So I'm sitting here, it looks like questioning authority or interviewing authority. Here's another nice picture. There's a bust of David Hilbert at the Netaji Leffler Institute. And in this picture, it kind of looks like Atle might be thinking about Hilbert's miraculous drum, saying that there's some problems there. I don't know. Here's another one. When you go on the Netaji Leffler Institute, further in the back, Netaji Leffler had some swords that he got. And when we were in there, I said, let's see if they're still there. And of course, Atle decided, let's get them out. This is a good picture. Mickey took this picture. Now, if you look carefully in this picture, I mean, it's clearly posed. But in the next picture, because I said something, now is your chance, Atle. Notice that he's not looking at, he started coming at me. And so, I mean, he had a playful side that it was a lot of fun. Okay, so then let me show you another picture. I got this picture from Jeff Mazaki. Sound mentioned in his lecture yesterday about Atle's result with positive proportion for a linear combination of zeta functions. And this is from Atle's lecture at Columbia University in 1998. He looks like he's in a very good mood. But I want to tell a little story about this. I remember when Atle and I were crossing the swords there, he was trying to come at me. I remember Mickey's comment. He says, said, when you two guys are together, you're like college kids. He said, I love it. Well, there's a story. That was true sometime. It was especially true in Sweden. In 97, this is from 98, in the fall of 97, Atle visited me for about 6 weeks. And he didn't want to give a lecture series, and he said, basically, I just want to give one lecture. And the department had said, you know, if we're going to pay him a good salary, he has to do something. So he said, well, I have him work with you. And I said, okay, I'll tell him. You're supposed to work with me. Now, we were a little short of money that year. The department had got a bright idea. He said, you know, if we say that Atle is studying, then we could classify this for tax purposes as a scholarship, and there's no taxes, and we can pay him some more money. So I told Atle, I said, the department head said, you're supposed to work with me. You're supposed to pretend you're a student, and he did. He said, fine. I'd like to go back to my 1942 thesis and try to see if I can get an unconditional positive proportion result for linear combinations. So since we didn't want to get in each other's way, I said, fine, you work online and I'll work offline. And I got my result first. He spent, as I say, about 2 months. He still didn't get his. He told me that a couple of times he was up to 2 o'clock in the morning working. He said, these estimates quite technical. I don't remember them like I used to. But after a few months, he called me. He said, I got it. So this was from shortly after that. Whether he would have got it if the department head didn't come up with his brilliant scheme, I don't know. Let me take there's another picture here. As Peter and others have said, after Atle got that result, it was like the theorem of the year by an 80-year-old, he lectured various places. One of the places that he lectured on was, they had this zeta function and random matrix meeting at MSRI in Berkeley. So, and earlier, Atle had lectured at this Vienna meeting on the zeta function. And this was at about the same time that Alan Kahn, there was this buzz about his proposed approach to the Riemann hypothesis with a trace formula. And I remember Peter and I and Atle were at the meeting in Vienna, and there were various degrees of skepticism expressed. And so at the MSRI meeting, Atle gave his lecture online. I gave mine about offline zeros. But then I told Peter Sarnak, I said, you know, I got an idea. Alan is not here. Alan Kahn is not here. Maybe we should send him a postcard. And so I said, let's go get Atle. So we notice, whoops, sorry. Atle said, wait a minute. I might mention, he said, that's a little strong. I asked Atle a few times, what if the Riemann hypothesis were false? He replied, the falsity of the Riemann hypothesis is an imponderable. So he said something similar, so in the next picture I put a G in front of it, and then we sent a copy of this to Alan Kahn and said, greetings from SRI. Okay. Now, the last thing, let me close with something. When I was preparing this talk, I was in Minneapolis, and I was looking through old reprints that Atle gave me. And I found one from 1979. It's a memorial speech that he gave in memory of Viggo Brun. I'd like to paraphrase the last two lines of this speech that he gave. And I apologize in advance for my very terrible Norwegian, or Swedish Norwegian, or some hybrid. So let me read. Atle Selberg som vi minnes idag var icke bara en stor matematiker, men också stor som människa. Hans minne gör oss alla rikare. La oss hedra detta minnet. Atle was indeed not only great as a mathematician, but also as a human being. And our memories of him do enrich us in spirit. Tack så mycket. Thank you.
Dear audience, the question I've been asking myself the last day is, why am I here? I'm here as a nephew. I was born 16 years or so later than Atle. I saw him in the later 30s, in the 40s, and until 1950 when he left for the United States. So the interaction is not the highest, but the thing I can excuse myself with is that I'm the only one who remembers his grandfathers, his maternal grandfathers, singing to us as children. And I'll give you an example, but later on, to keep the suspense. Yeah. I'll give you a quick introduction on the geography of southern Scandinavia. For the favor of Dennis Gotthard, I show Gothenburg. You have Oslo, Bergen, and Trondheim. The places which has connections to Atle Selberg is here in Langesund, where he was born. Then he moved to Voss, had time in Hardanger, which is there, and moved on from there to Bergen. And his parents then moved over when his father became a headmaster in Gjøvik, and then he made studies in Oslo. So that is his path through this. The reason for showing some of the other places is that there was a summer place in Hardanger, somewhere here, where the family spent much of their vacations. And the maternal line of Atle comes from this region here. The father's origin is up here. This is Bygstad, where the farm name of Selberg comes from. It's the farm closest to the church or chapel there, if you come by. Eikefjord, Oaksfjord, is a place approximately 20 to 25 kilometers north of Bygstad, with a distance which is all within that blue spot. So that is the outer setting. We have a PowerPoint presentation to come, but I have first given you this slide showing Atle's father and mother, his maternal grandparents, and the ones on the father's side. If we take the ones I have pictures of are the parents and these two grandparents. The ones over to the left on the father's side, I haven't been able to dig out anything from any of the families. His grandfather, Ludvig Axelsson Selberg, as well as all the other grandparents, were born in the 1840s. So it's a long time ago. No more than 50 years after the French Revolution, to put it in perspective. Ludvig Selberg, I have seen a document signed by him, by a very steady and good handwriting. And that was a census form filled out in 1890 or thereabout. And as opposed to his son, he didn't call himself farmer. He has, of course, farmed at this Selberg number 1 in Bygstad at one time. But I think that as this son is number 7 of 10 in total of children, So I believe that he, at one instant, found that he had to do something else to manage to feed all these people. So he again, just to take the father's line, it's no more important than the mother's line, but it's perhaps more important for the names in the family. This Ludwig was son of Atle Simonson. The address was Fauske. And he again was the son of Simon Nilsson, again with Fauske as the address. With Atle's grandfather's moving, with his moving from being a farmer and to do a little farming and very much else. And I know what he actually did at that time, because he declared himself as a independent operator in stone masonry and in barrel making. So that is him. He married someone of a family of some reputation, and his father's mother was a makeshift midwife. And midwives are not midwives because they are interested in the things in the middle of something. They are midwives because they are with wives. The woman who comes in and have some expertise and help with boiling the water and all that. The same faculties were within this grandmother, who also had a reputation for good hygiene, because she had volunteered at one instant to help the son of the district's doctor to nurse his son who had contracted typhus somewhere in the world. And she stood part of the job. She didn't get sick herself. She didn't spread it to the community, but the patient died regrettably. This is the only of these elderly I know anything about, because I have seen him and sat on his lap, and I'll return to that when we see the pictures of them. And I've used 10 minutes now. I'm sorry that this takes time. So yeah, well, you just switch. This is a picture you've seen several copies of before. I won't, they have been introduced, so I think we go on to the next copy of it. Here is his mother as a young, then educated teacher. She seems very sincere, and I think she is a beautiful thing. and she's also very beautiful and also very sincere on the next, taken many, many years later. She was a kind of rebel in her time, because she was in a family of 5, of which one died in his first year, or possibly at birth. And the 2 others also died in very trivial diseases that would have been cured with antibiotics and things like that in present days. One was 8 and the other was 11. So of the 5 children, only 2 came through it, and both of them lived to, my grandmother here lived to 97 or so, and her brother to 92 or thereabouts. Yes, this is her parents. This is Britt Skeie, this is Brita Bru, clad in a linen cloth of a starch type, used for festivities in Hardanger and the district where she comes from. A young Britt Skeie is there, and he must have been to a teaching seminarium or teaching college for 2 years in the 60s, 1860s. And my great-grandmother's chest for collecting all the necessary things for a young woman to take interest in staying on, either married or as a single person. This is Brita, Hans' daughter, Bru, and the year is 1861, and she was 17 at that time. And this is in my possession if you're interested. These maternal grandparents lived on a stretch of the Hardanger Fjord, and this picture is taken after my uncle Sigmund had been to the United States and shook hands with progress. So here is his Plymouth, what it is. I remember this place because Britt Skeie sat here, Atle's grandfather, sat here in the corner on his elevated porch. There were stairs up here, and when we in 1938, 37, 38 and 39 came running up and down the steps here, he sat in the corner and he sang in Norwegian first, jeg ser deg, men det kan ikke komme til deg. In English it would be something like, I see you, but I can't come unto till you. And he was having his stick by his side when he sang. It had a nice curved ending on top. He took that stick there and he fished us in. and there was a hug or two to be had. So my great-grandfather, I would say he was a lovable person and intensely also in search for love, because if you saw one of the first slides, he became a widower in 1915. He died in 1939, so there were 24 years in between. And he was exposed to some advances from the fairer sex, and his daughter and his son-in-law did all their best to prevent any scandal to occur. He was also I would say he was a beautifier of the world. I have a flamboyant examples of his handwriting and penmanship. And he was a master of ceremonies at weddings and funerals and at all other events in life. And yeah. I have already given you a little about it, but I would say that when when Atle's father called Atle's grandfather a farmer, that must be by a sort of Rousseauan thinking about the values of farming rather than doing everything else. And when if we say it's okay to call him farmer, you must not call him farmer in the North American sense, because the U.S. farmer is a homestead owner of 160 acres, and that is 640,000 square meters. And if these people were farming on more than 10 or at most 20% of a homestead, that is on top. And when they moved on to Oaksfjord at the end, they probably had a even smaller. This is Atle's father, and well, you can. That's sufficient. He liked to present himself as coming directly out of folklore or right out of rock. That was the image he liked to project to us. But of course, it's not as advanced as that. He was born the regular way, and he had 10. There were 10 siblings altogether in his family, and I know that during the years to come, he had a good deal of support from his eldest brother, Johannes, who was 13 years older than himself. He had much support from Atle Selberg, who went to Voss and opened a business there. And these people were sending off letters to one another and asked for 10 kroner as a loan for some time. Let me then give you a little about the economics here. I have the only part of what I say which is based on some sort of research is going back into my great-grandfather's notes on his income and expenses. And I choose three sample years with 10 years distance between them. And I started in 1892 and went up to 1912 when he retired. And if I convert his income with the rate of the dollar at that time, he earned $200 a year in the first station. In the next one, it had risen to $250 per year, and in the last one, it was $300 per year. So how could people survive on salaries like that? Well, it was very simple for Bricht Skeie, the maternal grandfather of Atle. He had the whole fjord basin to fish in. He bought a few lambs in spring and have them roaming about in the mountains with the lamb's mother, and but I think fishing and growing their own potatoes was a major source of food for them. And if you say $250 a year, it's probably what this person started at as a teacher in the lowest for the lowest age groups. And he kept a salary like that until he had, say, 3 children, and there came 6 more. So what did he do? Well, first of all, he had to qualify, because when he came out of the seminarium, he was told that this was not a fixed job. He had to qualify for it. So he had to take examinations in 2 stages, and the last one filling up the qualifications for entrance to university. And he did all these examinations as an external candidate. So he wasn't going to school. He was having school with his own pupils during that time, and but took the examination on the side. And this is a long jump. This is 1924, when his dissertation was the foundation for his doctoral degree. But there was a long way in between there. And if we take his most fruitful years, and this is incidentally the period of the First World War. He was teaching up to 47 hours a week, held summer courses for teachers, 2 exams for my Master of Science in Oslo, prepared for these mostly by night, improved the school's curriculum, improved salaries of teachers of my school, was elected member of the town council, planned the new school buildings, etc., etc. And of course, forgetting that he had got 2 children more to feed in that period. Yeah, thank you. Then and my time is run out, isn't it, Mr. Chairman? Yeah. Well, you should know them by now. Let's take them according to age and priority. This is Anna, my oldest aunt. She went into teaching on the high school level, and had a very strong interest in many directions, including botany, small-scale farming, and so on, languages, and whatnot. Then in 1906, this is Erik Selberg, became a mathematician later. This is my mother, Hjorthis. And incidentally, let me say that most of the children had ridiculous names. It's like a roll list for the Valkyria or something like that. My mother is Hjorthis Brynhild Åse Selberg, in the end. And who came next then? Yes, that must be Ingrid. That was a very strong character, and we know her today only through the anecdotes around. She was the only one who stood up against her father when she, the daughter, accused the father of handling the so-called twins, Sigbjørn and Arne, unequally. So, and she regrettably died at the age of 18 or so in 1928. Then we are on to the twins, Sigmund, firstborn, and Arne next, professor and mathematician, a professor in engineering mechanics. And when Niels Bohr doesn't acknowledge him as a mathematician, he would certainly attract protest from all his students from 1950 and onwards, at a time when he was the star attraction among the teaching staff at that time. So over 55 students in a class at that time, so something like 50 choose to take a specialization under him. This is Maya. Again, this is Magnhild. Yeah, you can get that name from me later. And then comes Ole Mikael, the same first name as his father. And he ended up as a lecturer in Nordic literature, but also with full command of German and French, at least for the high school level, and also with great cultural interest. So without having any special connection to the church, he was the only teacher and or other person in Trondheim who could sing old psalms, old hymns, in the way they were sung 50 years earlier. And then Atle, which we have heard a good deal about. My estimate here is that he is 4 years old, and if it's 4 years, this must be in 21, so then the picture is probably from Nestern, close to Bergen. Yeah. Well, after Ingrid died, the parents may have thought that it would be very nice to have a picture of the remaining daughters. And at that time, I think that Maya had got a sling of tuberculosis also, and was treated for that. So her studies in a teaching school were interrupted, and she never took them up again. The only one who rebelled was my mother, because she saw, let's call it, the suffering and the hardships connected with having such a huge number of children studying in Oslo. And even if he didn't take the money out of his own purse, at least some would have been taken there. And also he would have been a guarantist for all these loans. So I ask myself, who on a teacher's salary, at that time up to $300 per year, what would that correspond to? Well, I took all his expenses and I compared those expenses with the present rates, and I found that it all amounted to approximately $12,500 at that time. So you would probably not get any teachers with salaries like that. You are, how much are you? 5, 6, 7 times higher, isn't that right? Yeah. Some of that is, of course, regular inflation that's been all over. Yeah. This is the same the same 9 children after 2 have died, Ingrid and then the father. And this is on my grandmother's 90 years birthday. This is Anna again. This is Hjørdis. This is Maya. And many of you would recognize Sigmund, Ole, Henrik, Arne and Atle. This must have been in 63. No, 64. 1964. She was born in 74. So it was taken in 64. Yeah. The connection with Hardanger has been emphasized on one of the slides, the one showing my great-grandfather's house, which was taken over by Uncle Sigmund, represented here with his grandson somewhere. They bought in 28 or thereabout another summer house a kilometer further north and east, also on the stretch of Strandavann. And we are looking here at the fjord basin where the old man and his daughter's son Atle were fishing, did saltwater fishing. This is a view from the cherry garden, and the farm, well, it was 1 acre. The land here ended in a creek down there. There was a bridge. The family had no ownership on this side, on the painter side of the fence, but they had ownership of the green part here, continuing on to the other side. The house is not of interest. What is of interest is are the surroundings. First of all, there is a glacier, only barely indicated here, and can also be mistaken to be low clouds. There is approximately clear south down to that mountain there, 20 kilometers, and the glacier continues here, and it's remarkably stunning, in particular in May and June, when the apples are blooming and when there is still cold and dry. I didn't reach to say anything about the special faculties and interests. The brother Sigmund was known as a swimmer. The brother Ole, the one whose wooden horse had its legs chopped off by his younger brother, was a grand jumper, length jumper, not with starting with running, but just doing it from still. The brother Henrik was known in his young days to be painting, and he also continued later in life. And this, I think it's naive, and it shows respect and interest for nature, for the formations, and I think it has the naivety which my own things are having. So, please. This is Atle, of course, a picture taken at a photographic studio when he was 18 years. And this cap signals that he is ready to go to university. And he also did shortly afterwards. This is Atle at a later stage. I believe this is from my own garden, and this is from his moustache days. Yeah, well, this is actually signed by myself. This is a picture I gave Atle a copy of, and he said he would like to have it. So if it was good enough for him, it's probably good enough for you. And the title here is Redundant Numbers. So numbers are not only odd or even, they are not only prime and non-primes, but there are some redundant numbers. Stapled up, waiting in storage for one day being used. And if you allow something that might sound sentimental, that's a redundant numbers metaphor also for us who are gradually going out of history. But we are there, some of us stapled up in layers, and I think there is no more to say. But if they're especially interested, I can show you up details of the facts later on if you approach me. Thank you very much.
Well, up front, I should say I have two names. I've heard Mickey, which is what Atle called me, and my mother called me Betty. How that happened was a function of going away to school, and the freshman year at school is when lots of things happen. The summer of 1998, Atle sent a postcard to me, as you know by now, from China. He wrote that he was coming to Palo Alto and asked me to meet him for lunch at the Stanford Faculty Club. When we met, he said, I've been thinking that you should come to Princeton and share my house with me. And then he said, I will cook for you. I was stunned. I was happily retired from IBM. I was taking dance classes, and I was in the midst of painting the outside of my house a beautiful color. It's like dusty raspberry. No one else on the street has a house that color. I had left Princeton 16 years ago, and you know what it said, you don't go home again. But I was still excited by having lemons and oranges growing in my own backyard. So I was a California girl. I told him that I would come for a visit, but when we ran out of things to talk about, I would return to California. Also, I would bring my own pots and pans and cookbooks. And Atle did cook for me. He made pancakes and pea soup. He made poached salmon and boiled potatoes. He really loved cooking. Atle had a great memory for taste and for the way his mother had cooked. At Christmas time, she served lamb that had been dried in the wind. Atle often talked about this. You cannot bring it from Norway to the United States, and so all I hear is his words. She cooked both the large venison and the small ptarmigan. She flavored her sauces with goat cheese and lingonberries, and she let Atle help her in the kitchen. One Norwegian dish that Atle made for me was Hejhal, lamb and cabbage. He used only 4 ingredients: lamb neck bones, cabbage, a fistful of peppercorns, and water. All this he put in his pressure cooker, and in 20 minutes or so we had dinner. Now, I don't like the pressure cooker very much. I long ago got used to slow cooking. So I decided to find a better recipe for Hejhal. I put some chunks of lamb shoulder and some cabbage and peppercorns and chicken broth in a casserole and cooked it in the oven for a very long time. This was a new recipe from a very expensive cookbook. I served it to Atle. He tried to be polite, but he didn't like it. And I agreed with him. It didn't taste like his mother's Hejhal, and from then on we always had Hejhal made with cheap neck bones and water tossed in the pressure cooker. The Maxwell Lane house has many trees, and on a warm spring morning there will be large puffball mushrooms sprouting all over the lawn. One day Atle came into the kitchen with his hands full of puffballs, and he said he was going to cook them for dinner. I suggested this was a foolish thing to do because in the Midwest, where I'm from, we think that mushrooms growing on the ground are dangerous. The mushrooms you eat, you have to buy from the store. Atle assured me that all was safe. He brushed dirt from the puffballs, sliced them, sauteed them in butter, and then he brought them to the table. He begged me to taste them, and I refused. Instead, I wrote down the telephone number of the poison center. Atle ate the mushrooms with relish, but all night I was watching him carefully. I was looking for signs of blindness and paralysis and convulsions. Nothing happened. Atle laughed and assured me that he had a rough Norwegian stomach, and moreover, he knew all about mushrooms. Atle always enjoyed making his own birthday cake. I would bake a sponge cake base, and this Atle would slice in thirds, and on each third he would soak with sherry. Then he'd whip the cream and spread it on each layer, and then he'd pile the layers and put strawberries on the top. And this is the traditional Norwegian birthday cake. For his 90th birthday dinner last June, Atle's family came to Maxwell Lane with children, grandchildren, and spouses. We were 10 at table. For this event, Atle planned the menu. He served roast tenderloin of beef, poached salmon, potatoes au gratin, cheese grits, sautéed green beans, asparagus with oil and vinegar, tomato salad, gelato, and his own birthday cake. Ingrid served his birthday cake, and Lars poured the champagne. Atle did not eat very much at dinner. He could not swallow very well. But his eyes were full of joy as he watched his family celebrate at his table. He told me later he thought it was a good dinner. Thank you.